Welcome, everyone, to JADAK's webinar on improving speed and efficiency in your medical system using machine vision. My name is Justina Valencia, and I'm part of the marketing group at JADAK North America. With us today, we also have our presenter, Ken Romano, who we will get to in just a moment. Next slide, please. For today's agenda, I'm going to do a quick intro to JADAK and our parent company, Novanta, so you all can see why we are an expert on today's topic. And of course, I'll do a little intro about our presenter, Ken. We'll conclude the webinar with a Q&A session after the presentation for any of you who have questions about today's topic. We encourage all of you to type in any questions you may have into the Q&A window located at the top right-hand corner of your screen during the webinar, so I can read your questions to Ken once he has finished his presentation. Please be sure you are typing your questions to the host, which is me, Justina Valencia. This will ensure your questions are seen and read. We will do our best to answer all of your questions. However, if time does run out, we'll work with you to make sure your questions are answered via email. Next slide, please. So a little background on JADAK. JADAK is a business unit of Novanta. We specialize in machine vision, RFID, barcode, printing, and computing products, providing both off-the-shelf and optimized product solutions for medical device manufacturers. Since being founded in 2000 in Syracuse, New York, we quickly grew to be the Tier 1 supplier to the world's top 10 medical device manufacturers and now employ approximately 200 employees globally. Now, as this map up on the screen shows Novanta's global locations, JADAK's locations include the Americas, the Netherlands, China, and a recently new shared Novanta facility called the Novanta Center of Excellence in Munich, Germany. Next slide, please. So here's some information on why we are an expert on today's topic. JADAK was the first to implement embedded machine vision solutions into medical devices such as clinical analyzers, surgical machines, assay readers, and more. Our expertise is very strong in healthcare. In fact, about 90% of our business is with medical device manufacturers. Next slide, please. As far as Novanta, our parent company, Novanta's highly engineered and component and subsystem solutions and deep expertise in advanced photonics, vision, and precision motion make them a global technology partner of choice for medical and advanced industrial OEMs. Now, while Novanta provides innovative and enabling solutions within photonics, vision, and precision motion, JADAK falls into the middle vision group of Novanta. Next slide, please. And now the best part, a little bit about our presenter, Ken Romano. Ken joined JADAK last year in 2018 as part of the Imaging Solutions Group acquisition, aka ISG. He has dedicated 16 of his career years at ISG as a program and portfolio manager, so we're so happy to have him on board. He graduated in the top 5% of his class from RPI in Troy, New York. Now, in his spare time, Ken, not only does he play bass in a band, he also owns his own recording studio and records and produces music, which is really cool. So now I'm going to give the mic over to Ken, who's going to walk you through the meat of the presentation.
All right,
Enjoy.
Thanks, Justina.
Yep.
So let's get started. So we're going to talk today about how to use machine vision to increase the speed in a medical product. And that's a very broad category, so we're going to kind of focus on a few areas that we think have the most impact on increasing speed in a medical device or a medical system. Before we jump into that, let's talk a little bit about machine vision and what that term typically means, or traditionally it means. And in a traditional machine vision system, which you may be familiar with under that umbrella, it consists of a machine vision camera, and that machine vision camera may have industry standard interfaces such as USB 3 vision, GigE vision, camera link, coax express. There's several interfaces that are common in the industry, and they all have their niches and they have their applications where they work well and where they don't. There's often a cable from this standard camera a machine vision camera to a host computer or a vision system. And then there's the vision system or a computer, which traditionally has been used to analyze the images and actually perform the machine vision algorithms on the images to extract the data or tell the story with the image or find the result that you want to get from your image. So what that looks like, you have a camera and a cable and a computer or a vision system. And so the functions of these blocks in a traditional machine vision system, the camera is essentially there for image capture. And in your off-the-shelf standard machine vision camera, you're mainly using that camera to take the image from the image sensor and from your optics and format that data so it can be transferred over a cable via a standard interface for machine vision. So you have a cable between the camera and your computer or your vision system. And like we talked about on the last slide, the common interfaces, the most common interfaces today in the industry with are USB 3 vision and GigE vision are the most popular. You still have applications where camera link is used, coax express, and you see some emergence of 10 GigE vision and other interfaces. And then over here, this can be anything from a vision system that's tailored specifically for machine vision that runs a third party's machine vision software to a off-the-shelf computer running customers' specific software, or again, third-party applications, generic machine vision applications. So in a traditional machine vision system, some of the factors that are impacting speed obviously are how fast is your image sensor, and kind of coupled with that image sensor speed is the sensor resolution. So when you look at an image sensor of a certain number of megapixels, it'll have its own intrinsic frame rate. So how fast it can go, how many images per second it can capture. And then you have to transfer that frame rate, those frames over this interface cable. And so often a larger sensor with more pixels, you're going to be more restricted in frame rate by how fast this link is between your image sensor and your computer system. Kind of obvious there. And then factors that impact speed in the computer or processing system is mainly the processing power, the processing capability of that computer or vision system. So it's CPU performance, how much memory it has, how much disk space it has for storing images, and how often you have to access that and move things back and forth. So kind of all the same metrics that would be in play in any sort of computing system. I won't spend a lot of time on this. This is kind of just, if you look at those common machine vision interface speeds from USB 3 vision and GigE vision, you can see what the speeds are there. And these are kind of what we consider the high-speed industry standard interfaces that are available today. And some of them have been around since around 2000. And this is kind of the key interfaces that are available in the market today for a traditional setup for machine vision. So one of the things we want to do is look at how can we use embedded machine vision to kind of reduce the system processing requirements, to reduce the post-processing to increase the overall speed in the system. So before we jump into that, let's look at medical products specifically. So you're seeing more and more use of vision, of image sensors, of embedded cameras in medical devices increasingly. Some of those applications are obviously endoscopy and disposable endoscopy. Traditional endoscopy, often there's a scope with an optical path and a camera control unit with an image sensor and the electronics and the image processing to process images there. In disposable endoscopy, you're starting to see the emergence of tip mounted image sensors, small diameter sensors where the image sensor is in a low cost plastic molded enclosure, and all the image processing is done in a camera control unit, but that endoscope and its image sensor are often a completely disposable one-use type of application. IVD systems, this is an area where JADAK has extensive experience and a lot of applications where you're looking at a test tube, you're measuring the liquid levels in test tubes, looking at the color of the cap, you're reading a barcode on that tube, you're looking at samples. Diagnostic imaging, this can be looking at tissue samples on slides. This can be actually looking at a patient real time. Um, looking, for example, at the retina in an eye exam. Um, Another area that imaging is being used is blood and fluid analysis. And we're seeing more and more calls for low-cost point-of-care type imaging applications using cameras and using imaging sensors um, in a doctor's office type situation. So you're seeing more and more use of cameras, image sensors, and image processing in medical devices. So embedding machine vision in medical products, some of the key drivers that we hear from customers are obviously system cost. Even in a medical product, that's like in any other market, that's always an extremely critical driver. Obviously, accuracy. If you're going to make a diagnostic decision, your color has to be accurate. The image has to be clear. You have to have enough resolution to discern the features you're looking for. And often, more and more too, we're looking at speed being a key driver. So, and that speed can mean a lot of different things. That's what we're going to kind of focus on today, what we mean by speed and how to use embedded machine vision to improve speed. So the common customer requirements that we see is integrated systems. So if you remember back to those first few slides, we talked about traditional machine vision systems being an off-the-shelf camera, a cabling system, and an image processing computer or imaging system. And in a medical product, you may want to integrate all that into one system so that they're more tightly coupled, lower cost. And also, along that same line, we see a lot of push for lower cost interconnects. So we want to use standard interfaces that would be available for example, for free on a motherboard or on a single board computer. You know, the ports that would be there anyway, without having expensive things like frame grabbers or interface cards in the machine. So you want to embed and use low-cost interconnects and standard interfaces. More and more, we're seeing requirements for small footprints. Again, some of these applications can be battery operated and handheld. Small footprint, we're seeing calls for things like tools that will look sort of like an endoscope, but they're for ENT or for looking inside the ear. And all of the image processing, all the image sensor has to be in a very small package. So small footprint is also very important. And low cost embedded processing. So you see lots of industry trends around things like media processors, which integrate a lot of CPU capability into a small board. From the educational market, you see things like the Raspberry Pi, NVIDIA boards now with a single very powerful processor. So we want to use low-cost embedded processing as much as we can. Everyone's very familiar in today's market of what you can do on your iPhone or an iPad and your cell phone with imaging, with the camera capabilities, and more and more of our customers are expecting that level of tight integration and small form factor, but they want advanced image processing and machine vision features in their device. And so when you look at all that, we kind of we're going to kind of look at machine vision in medical products as embedded machine vision. You'll hear terms like embedded vision thrown around now, and that's really kind of looking at where the camera function, the processing, and the machine vision capability is integrated and embedded in the product, as opposed to using a lot of large off-the-shelf components. So what are the reasons why you'd want to increase speed? There's just a few of them. There's many more, but the ones we'll kind of focus on a little bit today and give some examples to illustrate our point are one of the big drivers that we see from customers who are doing real-time surgical visualization type applications. And this may be endoscopy, this could be borescopes, this could be anything where a doctor or any sort of technician is looking at the image real time while they're moving a scope or another imaging device into the patient or around the patient, surface skin, ENT, like we said, all those applications. Low latency imaging is extremely important to that. So if a doctor is moving a scope, they want to see that the image on the display that they're viewing feels like they're seeing what's happening real time. And so you want to keep the latency of the image processing and the latency of that displaying that image as low as possible. Another big driver for speed is to reduce examination times. So that may be, having someone sitting in front of a machine that may take an image of your retina. You want to take a lot of high resolution images and get all your data before someone blinks or before they're fatigued sitting in front of an examination machine. And for IVD applications, you want to be able to process a lot of samples very quickly with high accuracy. So speed becomes important in all those types of applications. And so how are we gonna focus on increasing speed? And so when we look at what affects speed in an image processing or machine vision system or any system that's analyzing images or using video data, one of the big areas is to reduce the interconnect bandwidth requirements. So if there's any way you can reduce the amount of data transferred between the camera and the host computer or embedded control system, you're going to be able to increase speed and efficiency. If you have an embedded computer, you're trying to optimize its use. It may be doing a lot of functions in your system. Reducing the amount of CPU cycles needed to process and analyze images will in effect increase your speed because you don't need to devote as much processing time to that function. And another area to reduce interconnect bandwidth requirements and increase speed is to tightly couple the image sensor and the image processing to eliminate inefficiencies that are every time you go through an interface or go through a cable or go from a board to board connector. If you're tightly coupled, you're gonna maximize your efficiency. So how do we use machine vision and embedded machine vision algorithms to reduce interconnects and cabling requirements? So what we're going to focus on today, and this, like I said, this might not be the only way to attack this, but the one we kind of want to illustrate and talk about today is using camera-based optimized application-specific image processing. So this is image processing and machine vision algorithms that are very tightly tailored to the customer's application and what you want to extract from that image. And kind of a key to that, one of the key blocks is to use a pipelined FPGA architecture for the image processing blocks combined with low-cost embedded media processors. So we'll talk a little bit more about that in the block diagram section. And kind of key to this approach also is to the embedded CPU, the FPGA, and the image sensor are tightly coupled. And this may be on a very, when I say tightly coupled, they could reside all on one circuit board or one or two circuit boards, but an integrated system that has a very tight form factor with all of these elements, integrated close together. Another way to approach this that we've been doing at JADAK over the years as well as the previous company before we were acquired, was to build a library of common imaging operators for quick time to market. That goes all the way from barcode engines and decoders to algorithms that could detect color, that detect features, standard machine vision type operators like blob detection, all the way to a color pipeline to process high quality color images at like a digital still camera level quality, and do these in pipelined FPGA blocks for maximum efficiency, and have this library available to reuse and modify for quick time to market for our customers. And so kind of the way we're looking at it is a highly optimized embedded machine vision system, which is different than a generic smart camera that could, run any code or have a large library of generic operators that you call. This is more of an optimized for the specific application. So application specific and tightly coupled to the desired outcome. So what do embedded machine vision architectures look like, the type that we're talking about today? One example is what we show here, where we have an image sensor, and the image sensor obviously is what converts the light, converts what we're looking at into pixels and into data. Integrated LED lighting to light the target in many cases. And then you'll see this image sensor is directly coupled to an FPGA in many cases, and this FPGA can do all of the sensor calibration and corrections. We can have a full color image processing path that can do everything from color correction of the image, white balance, the demosaic of the Bayer pattern, and actually create in real-time pipelined hardware with very little latency a full color image that can be viewable or used to do further downstream machine vision and image processing functions. In the same FPGA, we look at the customer's application, and we can create other blocks or modify blocks that we've had before to do customer-specific image processing. So that's tailored to the actual specific implementation or the algorithms or things the customer needs to do in their machine. And then another piece of this architecture, we'll use a low-cost embedded CPU. That can be a media processor like the IMX series. That can be a very low-cost embedded ARM processor, that includes things like a USB 3 interface driver. And these embedded CPUs can implement machine vision code as well as compression, system communications, and then we kind of look at what we optimize every application. We look at what makes sense to do in software and the CPU, and where can we take advantage of what the FPGA is really useful, really good at doing to increase speed. And then these embedded systems, we want to use an off-the-shelf common low-cost interface like we see on all motherboards or single-board computers, using something like USB 2 or 3 or Ethernet, or in some cases that can even be a simple serial port if what we're doing in the embedded system over here can do all of the image processing, all of the machine vision, and just output results over something as simple as a serial port. Another example of an embedded machine vision architecture that's very efficient is we're seeing more and more, like I said, handheld products, or products where all of the system control and all of the system electronics is embedded in the machine vision device. And in this case, our embedded CPU that talks to this FPGA and may do some of our machine vision and our image processing also directly controls the display and any inputs from someone using the device. So it's a truly integrated system. It may have storage devices connected to this. You can drive an LCD display directly, a touch screen, have keyboards and switches integrated. So in this case, our embedded machine vision system is the entire platform or the entire system electronics for the product. And so to kind of illustrate this in a little more detail, we'll look at one of these architectures and how speed is improved or impacted by each block in this architecture. And then we'll look at a couple of use cases or examples of where we've employed this architecture to increase speed for our customers. Sorry, this slide's a little busy. Some of this text is a little bit small. But so if you went a couple slides back, we talked about an embedded machine vision architecture that had a tightly coupled image sensor, FPGA, embedded CPU. And so what areas do impact speed in this type of architecture? Obviously, the sensor interface, and in a lot of our applications, or most of our applications, this sensor interface is directly coupled to our FPGA. So this FPGA can have multiple channels out of this image sensor for very high speed. On a circuit board, you can have up to 16, 32 channels out of some of these image sensors, or if you had to move that over a cable, you'd have a lot more difficulty than these short circuit traces with high-speed interfaces. We use high-speed interfaces here, multi-channel LVDS. There's a new emerging standard, SLVS EC, which is a low voltage LVDS with an embedded clocks. It allows us to go even faster between the image sensor and the FPGA. So a key area for speed is that interface between the sensor and the FPGA. And then the FPGA is a key area of how we approach a lot of these applications. So within an FPGA, you can look at the FPGA as like a programmable hardware device. So in that programmable hardware device, you can link up pipeline blocks of image processing or machine vision hardware accelerators. And since they're pipelined, they're like a sequential and real time and all happening at the same time. So as you process, say you're doing a filter or a function on the image sensor, from the image sensor, on the data from the image sensor, you pass the data from one pipeline element to the next, and each one operates on its context of pixels and then passes that on to the next block. And so you can create very low latency fully processed images. So you're not doing something like moving each plane of data into the memory and then having different pieces of software access that one pixel at a time. So the FPGA is very good at that type of processing, things that are moving a filter through an image, operations that operate on every pixel, and that type of on-the-fly processing is what they really excel at. So we gain a lot of speed using the FPGA in these with a pipelined accelerator type architecture. The CPU, it makes control loops and decisions based on FPGA outputs. It can use data that was processed by the FPGA to do further machine vision work and further operations on it. And there are some machine vision algorithms that really work better in a processor than an FPGA. So sort of key to our approach when we look at an application is to kind of figure out that ideal partitioning of, which functions and which blocks can be done in the FPGA or which should be done in the CPU, and then optimizing that selection and that partitioning for speed. And so the result of being able to do that processing, make those decisions, and embed those algorithms in this embedded machine vision system is we can reduce the bandwidth that's required to move over a cable, and also reduce the computing load on the embedded computer or the system controller. It has to do less. So we can only send results to the system controller, after we've already processed it and extracted the data we want to get, or we can send pre-processed images that have already been optimized for the features we want to extract from those images. And so we're basically reducing the amount of bandwidth in many cases that's required over that link, and reducing the amount of CPU cycles needed to process those images in the host computer or in the embedded computer system in the product. And so the result is higher system speed and efficiency. So I guess the proof is in the pudding in some way. Let's talk about where there's actually been, where that's been used to become effective, and where we've actually demonstrated speed increases using these approaches. So here's a case study. We have a few applications that are using a similar type of architecture with a similar problem statement or a similar need for speed and acceleration. This case is surgical navigation. And so what you're doing there is you're basically using a stereo camera pair, um, two image sensors, two cameras to look at a left and right image. And you're looking for example, on a surgical tool for a marking or some kind of key. And you're tracking that tool in space because you've either you have a surgical plan or you have a plan for an operation and you want to make sure the doctor is following that plan, or all the way to eventually having true robotic surgery where there's a plan that's stored in an AI type device that's actually performing the surgery. Um, and then these in the one of our customers came to us with a system that they built using two cameras, and they had their host computer was processing raw images from those cameras and looking for their tracking marker in those images, and then generating where the tool is in space based on the stereo image from those cameras and that marker on the tool. And so with that system, they were able to achieve about 5 frames per second of tracking accuracy. Um, and they had to use two independent cameras, two independent USB 3 cables to control and get the data and control the cameras. And the result was they were able to do it with a fairly powerful host computer at about 5 frames per second, um, which a few years ago was still kind of a leadership product. But at 5 frames per second, you're not going to have a true real-time feel for a surgeon. You're going to feel some lag. You're going to feel some jumpiness in the image and the feedback you're getting from where that tool is. And so using our approach for embedded machine vision, um, we developed a system where we have two image sensors, and these image sensors are directly coupled to our FPGA using the high-speed LVDS interface we talked about. And we looked at the algorithm, and we found that big portions of that algorithm that are used to find that marker, find that tracking symbol, um, work very well in an FPGA and a pipeline hardware architecture, since to find those markers, you're basically processing and doing algorithms on every pixel and on groups of pixels. It was an ideal type of algorithm to implement an FPGA. Um, so now the FPGA is implementing the tracking marker detection in real-time pipeline hardware. So basically at the full frame rate of the image sensor, we're finding the candidates of what could be their marker. And we're just passing those candidate regions for the marker to the host computer. So you get a lot of benefits for speed and efficiency by doing that. So obviously, if you're just passing what looks like the markers on the tool, you're eliminating most of the image data. You're only sending the relevant regions of interest. And so you're increasing speed by sending a lot less data over that link. And then the host computer only has to look at those regions that are potentially the target. So its amount of CPU cycle processing is vastly reduced to where you're looking at only 10% of the data, for example, in the image, where you used to have to process and examine all of it. And so with this application, you move from a 5 frames per second limitation to a speed increase of 60 frames per second, which is 10 to 20%, 10 to 20 times improvement, and now gives you a true real-time feel. You don't have any lag, you don't have any jitter or stutter in what you're doing. And so a surgeon using this to assist them in a surgery is going to feel that it's real time and feel that the system is working as fast as they are. And so, and there's other benefits, obviously single cable and a lot of reduced bandwidth. So there's one application where you vastly increase speed by embedding this machine vision and embedding this image processing in the FPGA. Another application where we've used a similar architecture is one of our customers is using is doing basically cancer treatment visualization. So the idea is to be able to create a visual image of where a beam of radiation is hitting a patient for treatment of cancer. And in the prototype system, we use one of our standard cameras, our off-the-shelf cameras that we have, and an intensifier from that camera, and we create a very low level but a visible signal of where the radiation is going. And in this application, the host computer had to take these frames and do quite a bit of processing to actually find and see that image of where the radiation is hitting the patient, and then superimpose that onto an image, a real image of the scene of the patient in the treatment machine. And so there was a bunch of image processing algorithms that we did that were done first on the host computer. You acquire a background frame, you acquire multiple active frames of image data that include this signal that is a radiation and see where it's hitting the patient. You have to subtract the background frame and apply a couple of custom filters actually, and several operations in that. And those custom filters are there to reduce the noise. It's a very noisy signal, and to intensify the signal of the radiation, what you want to visualize. And then do some frame averaging again to reduce noise and to increase the signal level. And then sequencing the background frames and foreground frames and active frames. So you want to actually, when you're viewing this on a display, you want to be able to view the patient in the treatment machine, and then you want to be able to also see where the radiation is hitting the patient. So you have to kind of sequence in and out the frames of the patient and the treatment. And so their demonstration of the technology was done on a host computer, and it was done non-real time, but it proved that the concept could work. And then what we did was we looked at, again, using that FPGA to accelerate those functions so that the system could actually operate as a real-time product. And so the FPGA performs all of those image processing blocks in a pipelined architecture. So you're not, basically it moves from one block to another at near real time. So we apply, we take the image from the sensor, calibrate that image, apply the custom filters, first custom filter, second custom filter, do the frame averaging all in the FPGA with its embedded memory, and then sequence those frames of background frames and foreground frames all in the FPGA, and then actually transmit this to the host computer at a frame rate that allows live viewing. And so the host computer now is only there to display the image, present the user interface that the company wants to present to the doctor, allow storage and capture of the images. And so again, we've used this FPGA and these pipeline hardware architecture here in these blocks to bring the speed level up to where the product is viable. So there's a couple of examples using the methods to increase speed that we talked about. So in conclusion, looking at those points of where we're going to attack this problem of speed, camera-based, optimized, application-specific image processing, this gives the customer a performance advantage. So if you're a company and you want an advantage in your market for speed or accuracy, if you have optimized embedded machine vision, you could be ahead of your competition. They may be using the off-the-shelf camera, computer-based standard machine vision toolkits, and you can jump out ahead of the competition by using something, an embedded architecture like this. Utilizing pipeline FPGA image processing blocks with low-cost embedded media processors. This is the highest speed approach when you optimize that CPU and FPGA task load. So kind of the key and kind of the expertise we try to develop here is to be able to look at a customer's image processing and machine vision algorithms and decide what's best to be done in the FPGA and what's best to be done in the CPU. And if you get that right, you really get a huge advantage in speed and efficiency. And again, embedded CPU, FPGA, image sensor are tightly coupled. You don't lose transmission data bandwidth, or you don't have to force all of your data onto a single wire for a long cable. You have the most flexibility and the highest speed between those blocks. Um, and our goal is to build a library of common imaging architecture. So when a customer comes to us, we have a large library to start with. We may have to create some custom blocks for their custom algorithms. So we may have to protect those custom algorithms as theirs only. But we do have a big baseline of blocks to start with that we can recombine and hit many, many of the applications. And this, like I said, this is everything from FPGA hardware blocks that are ready to go to software and machine vision modules and blocks, what we use in our Clarity products. This could be everything from barcode decoding to standard machine vision, color detection, all sorts of library elements that we reuse in these products. And then again, highly optimized for the application. We're not talking about generic smart cameras. And when you highly optimize, you can really pick the right image sensor, pick the right size FPGA for the application, size the CPU properly, the number of cores, so that you have essentially you have what's optimized for the application and not just a generic smart camera that's intended to hit every application. Um, so that's kind of the approach, and why we think it's a good way to go for increasing speed. So I guess turn it over to Justina now for questions.
Thanks, Ken.
Sure.
So we did have a few questions come in, and I would just like to ask anyone at this time to please type in any questions you may have into the Q&A window and direct them to the host to make sure I see them and I can read them out loud. So Ken, the first question we received is, aren't FGAs cost prohibitive for embedded applications?
So actually, they're not. So FPGA technology is one of the electronics technologies that's moved the fastest over the years. So the amount of gates and amount of memory you can purchase in an FPGA in the last 5 to 10 years has really increased dramatically. And also we look at that FPGA and we size that FPGA for the application. So the FPGAs can be very low cost, under $20, very similar to a low cost embedded CPU, and accomplish a lot of functionality today. So yes, if you were to look at the FPGA and buy a generic FPGA that can do everything for everyone, they can get expensive. But we've kind of made it one of our key focus areas is to optimize and select only enough FPGA for the application. We also have standardized on a few low-cost devices that we use in many, many products. So we've negotiated special pricing on those devices. If we're using one of those, we have a very, very good price and can create a very low-cost product.
Okay. Another question that we had come in was, are FPGA-based implementations less programmable than software implementations and harder to change?
Um, so FPGAs are essentially programmable hardware. And the way we design our FPGAs, we actually use a hardware description language that looks a lot like software code. So there's several ways to make the FPGA-based architecture programmable. One of them is all of the image processing blocks and machine vision blocks we would implement in those FPGAs are parameter based, and so you can set them. You can program the parameters of those, and that's programmable. And so, for a color space transformation, or let's say a color filter, where you're doing a color transform or applying a matrix, the FPGA is implementing that in hardware, but all the coefficients are programmable. So we design those FPGA blocks so they're programmable hardware blocks. The other aspect of that is the FPGA, the P in the second letter there is programmable, so it's field programmable gate array. And so even if you had to change your FPGA code and redesign that FPGA, that's something that can be field loadable. So we can reflash the device and we can program that FPGA with new functionality or change functionality even after the product is installed in the field.
Okay. Does this approach require custom hardware for every OEM application?
So no. In about 50% of our applications, we're using our platform products as is, the hardware as is off the shelf, and basically customizing the firmware for the customer. So we have our Allegro series of cameras, and even though they'll look like a off-the-shelf machine vision camera, we often develop custom firmware for those cameras to make them specific to the customer's application using off-the-shelf hardware. And we're developing some new products aimed specifically at the IVD market and some new camera series that we'll be talking about soon. That'll also be new platforms at lower price points that will not require custom hardware. Some customers, they come to us and they definitely want a custom form factor. Um, and so, in those cases, yes, we'll do custom hardware, but it's not always needed.
Okay, another question we had was, have you run convolutional neutral networks on FPGAs?
So we haven't yet. So that's an area that we're looking into and examining what type of FPGA and what family to look at to do that. So that's something that we're going to be doing in the future.
Okay. I believe that is all the questions we had. If anyone has any more questions, I'll just give everyone a few seconds to type in anything that they might want to know further. Okay. Ken, if you could just go to the next slide, please. Okay. Everyone, just up on the slide, we have our upcoming events. If you're interested in seeing our machine vision capabilities live, we will be at the Embedded Vision Summit in May in California. Then we will be back out in California in the Anaheim region in August for the annual AACC trade show. And then lastly, we'll be co-exhibiting with one of our sister companies at Medica in Dusseldorf, and details on that are still forthcoming. As far as other events, we do have another RFID webinar coming up, and that is April 17th. Also, be sure to check our website or social media channels for more information on our events and other upcoming webinars. Next slide, please. I would also just like to mention for all of our European listeners, and you may be already aware of this, due to GDPR, we are unable to send you a recording of this event. So if you would like to receive a recording of this event, please email us at opt-in@jadaktech.com indicating we have your permission to send you marketing information. Or you can download a recording of this session from our website under the resources section, and the recording will be available March 29th. At this time, I would like to thank everyone for attending our webinar today, and I hope that everyone has a great day.